Okay, so we're going to talk about the central limit theorem, kind of a cool way of getting something back into what we know. We know a lot about normal distributions, but not everything in life falls under normal distribution. A lot of stuff does. So what we can do with the central limit theorem is we can make skewed or non-approximately normal data into normal distributions. When we do that, we're able to use the 8 tests that we learned about, the control charts. We can find z-scores and things like that. So the scenario I'm going to use is the spinner from 0 to 9. And we're going to run a bunch of simulations to see what the data would look like and how we can use the central limit theorem to change our data and make some conclusions past that. So if you think about what the probability of getting each of these, it's essentially 1 out of 10. There's 10 different numbers here. You can get any one equally likely. So if you run a simulation, which I'll do here, that's what this does. If I just take 1,500 runs and I conduct that, and it's just doing the data for one, find the mean of one data point, it's just plotting it. As you can see, pretty uniform. Straight across the board, pretty equally likely. I got a couple more 5s it looks like than the other ones, but if I did this again, I conducted 1,500 more runs, it's going to get pretty much uniform straight across the board. So we can't find normal distribution shape or use any of those tests. So what I do with the central limit theorem is I take sample means and then plot those on an X bar chart. That should have a bar over it. But for example, let's say I roll a 2 and a 7. So that sum would be 9 and then divide by 2. So I would get a 4.5 and I pop the 4.5. And then I roll 2 more numbers and I get a 0 and a 5. And then that sums 2.5. So I'd plot all these values, but I'd do it a whole bunch of times, like that 1,500 runs. So this is what that simulation would look like. So now I'm going to do means of 2, not 12, 2. So first I want to show you this actually. Let's do one run again, pretty uniform. If you go to means of size 2, look what happens. 2 numbers at a time, and look at that. Just by finding the mean of 2 numbers, the shape gets pretty approximately normal. From here then, if I do a mean of 3, watch what happens. So that's doing 1,500. It's picking 3 random numbers, finding the mean of it, and then plotting it. And as you can see, the larger my sample size becomes if I take 4 numbers at a time rather than 3 numbers and conduct all those runs. I think you can see what's happening. 5, and there you go. I mean that shape is definitely approximately normal. And that's even more clear that if I take sample sizes of 6 at a time and plot all those runs, it's approximately normal. So again, here's just plotting all the points, plotting all the numbers should be uniform. And if I take sample sizes of 6 and I do that again, it's really, really, really close to approximately normal. So from that, what we conclude with the central limit theorem is the larger the sample sizes that you take each time, the more approximately normal the distribution is. So that's the nuts and bolts. We might want to know why this works and just think about finding the mean of certain numbers. For example, if I'm taking 5 numbers at a time, pretty large sample size, but the probability of getting all zeros is really, really low. So that one's not going to happen very often, so that's why it doesn't happen that much in the distribution either. The mean of that is 0, so getting a mean of 0 is actually a lot harder than if my numbers are all mixed up. I got a 0, a 4, a 2 3s, and a 8, whatever it is, more randomly. When I find the means of those, what happens is it gets extremely close to the mean of these numbers, which would be 4.5 also. So that's kind of a cool thing that from these 10 numbers, the more numbers I take, the mean's going to be closer to the actual mean of the numbers, individual numbers. And there's going to be a little bit of variation. It's really hard to get all zeros, or it's really hard to get all of one number, actually. But on those tail ends, when I have 5 9s for an average of 9, that's really low probability, so it doesn't happen as often as it would for these middle means. So again, or lastly, I should say, look at this. This is amazing. Uniform, straight across, take sample sizes, let's do 5. 5 at a time, find the mean, plot them, and it's approximately normal. I think that's pretty cool. So hopefully this helps just understand what that central limit theorem is, how we do it, and then a big conclusion we're going to talk about is the larger the sample size you take, the more approximately normal that distribution is. Hope this helps. Have a great night, day, wherever you are.